has 4 presentations for the 2 hours, so you will have more or less 20 minutes of presentation, and you can have 5 minutes to ask some question. And please, if you have any question, feel free to fill the discussion part of the Zoom conference due to the fact that all the microphone are switched off. For the first presentation, we welcome Emmanuel Hache. Emmanuel holds his PhD in economics from the University of Paris 1 and a Master of Science in Development Economic and Sociology from the Institute of Study and Economic Development and Social, also in the University of Paris 1. He also holds a master degree, a Master of Science degree from the Institute of International and Strategic Affairs in Geopolitics and Foresight. He has a tour of experience in India. He became a research fellow in economics, specializing in commodity markets for the Center of Economic Observation, COE. And in 2006, he joined the IFPEN school as an associate professor. He will talk about the prospective in global value of lithium-ion battery, a criticality analysis. So Manuel, the floor is yours.
Thank you for this introduction. Do you see my screen?
Yes.
And my presentation? Okay, that's perfect. So thank you for this introduction. Just to tell you that we have changed a little bit the name of the presentation because, you know, since last year, we have broadened the scope of our work dedicated to criticality. And of course, I will talk about the materials components of the battery, and I will talk about criticality. But I will talk about also copper, cobalt, nickel, aluminum, and more generally for low carbon technologies. And the work that I will present today is a teamwork that I realized with my colleague Gondia, Sokhna, Seck, who is energy modeling specialist at IFPEN Energy Nouvelle. So a brief outline of my presentation. I will make a very short review of literature. I will present you the model that we use for the methodology, and I will present you after that the result, and I will make a very short conclusion on the work we did. So let's start by a very short review of literature. You know, I don't know if you know a lot on criticality, but criticality and all the stuff related to raw material supply risk have been widely discussed since the past decade. But what I will say is that an extensive part of the literature was devoted to rare earth elements, or what we call green metals criticality. When I say green metals, I talk about cobalt, I talk about lithium. And the fact is that in our work, we have also decided, you know, to look at structural metals such as copper, nickel, or aluminum. And one of the major challenges that researchers can have, you know, when they work on criticality is which methodology can we use in order to assess the risk for the different commodities. And more especially, you can focus on geology, you can focus on economic, you can focus on geopolitics. And the fact is that what we try to do in our work is to focus on all these fields. But today I will present you only the geological part of our work. Otherwise, I will need 40 or 1 hour, you know, to present the complete work. What is the originality also of our work? It is the fact that we use a partial equilibrium model that we started to develop in 2010 at IFP New Energy. But I will present you the model model in a few minutes. But what is interesting also regarding the originality of the paper, it is a fact that when you look at the other articles, they focus on the past, they focus on what happened today, but there is not a lot of articles dedicated to what could be the cumulated or the cumulative demand of production for the different materials, for example, in 2050, depending on different climate scenarios. And this is what I'm going to present to you today. So let's just talk about the model in a few minutes. So as I told you, we use a Times Markle model, which name is TIAM IFPEN. This is a world model. This is a partial equilibrium model. The objective function of this model is to minimize the cost of the entire system. The model is disaggregated into 16 different regions, and on each region can trade fossil fuels, can trade also materials, can trade emission permits. And what is interesting, and you can see that in the figures, it is the fact that all the technologies, I mean conversion technologies, are also represented in the model, such as the different sector, I mean industry, commercial and services, household, transport. And on the right, you can see that you have the demand. We compute exogenous demand in the TIAM IFPEN model. And the main question that this kind of model can answer, it is question dedicated, for example, to climate change, but also to security of supply, and more especially for security of raw materials, and more globally to a feasibility or condition of feasibility for the energy transition. I show you just very briefly, for example, how we disaggregated the transportation sector, because we'll talk about battery. And in our model, we have, for example, different technologies. We'll have a passenger car, bus, minibus, commercial vehicle, 2 and 3 wheelers. And for each type of car, for example, you will have different ranges of cars, small one, medium one, large one, with different kind of motorization and for sure different kind of fuels. And also, in order to assess metals criticality, we implemented the value chain of each metal within the model. I give you an example for the lithium on the left and for the copper on the right, but this is the same kind of modeling that we use. It means that we evaluate the resources. We put all the resources, I mean conventional, non-conventionals, and we put also conversion processes with energy cost, emission, and we implemented also trade. I mean that for example, in lithium, you can trade the ore or you can trade the oxide, and also we have the same kind of stuff that for sectorial demand. So what is the aim of this kind of model? It allows us, to evaluate the consumption of materials with regard to the deployment of the low carbon technologies, but also the trades of these materials between countries at different points of the value chain. And also, in order to do this, you need to implement the material intensity for each of the low carbon technologies. I mean, for electrified vehicle car, but also for wind, for solar, etc., etc. And what we did, we ran 4 scenarios where we have considered 2 climate scenarios with 2 different types of mobility. The 2 climate scenarios, we have one, what we call 4 degree. This is a 4 degree scenario. What does it mean? It means that we are limiting, the expected global average temperature increase to 4 degrees. For the 2 degree scenario, this is exactly the same thing, but we are limiting, the global warming to 2 degrees. And for each scenario, we also add 2 different kind of shape of mobility. what we call a high mobility or a business as usual mobility, and also an hypothesis of a sustainable mobility. What is a sustainable mobility in our case? In the case of our modeling, it means that we'll have a very, very interesting optimization of the transportation system, but also public policy directed, to public transportation is added, etc., etc. So the results. First part, the global result of the system. We have, when we run the different scenarios, you can observe the evolution of the global fleet between 25 and 2050. Which conclusion can we see? If you compare, for example, the 4-degree scenario with the 2-degree scenario, for example, for business as usual mobility, you can see that on the left here, you have 21% in the fleet, which are electrified vehicle. If you go to a 2-degree scenario, you can see that 50% of the fleet is electrified. This is the impact of the climate constraint. If you look now at the differences between business as usual mobility and sustainable mobility, you can see that we have less vehicle in the case of sustainable mobility in both scenarios. I mean, for the 4D scenario, but also for the 2D scenario. And if you compare the results that we have, regarding the number of electric vehicle in 2030 compared to a number that we can find in the literature, more especially from the International Energy Agency, you can see that we have between, depending on the scenario, we have between 130 and 180 million vehicles, and you can compare it with the International Energy Agency numbers. We observe the same kind of deployment, of low carbon technologies for the world power sector. You can see that in a 4-degree scenario, you have an increase of low carbon technologies, but if you go to 2-degree scenario, you can see a huge impact regarding, for example, wind or solar. And what is important to mention, it is the fact that, as I told you, a low carbon technology can have a higher materials intensity than traditional technology. So if we look at the first example related to lithium, lithium is widely used, in lithium-ion battery. And if you look at our results regarding, for example, cumulative production, you can observe the cumulative production, for example, for the 2D scenario or for the 4D scenario with at each time, the different shape of mobility. You can see that if you compare 2D and 4D, you will have much more mine production of lithium in a 2D scenario. But what is interesting also to look at, it is what about geological criticality? I mean, what is the amount of lithium that we will produce, and can we compare it to global lithium resources? And this is a number that you see here. How to deal with the 32%? It means that between now and 2050, we will consume around 32% of global lithium resources. I do not talk about reserve, I talk about resources. And we took resources because reserves can move depending on technology, on the price, but resources are more consistent with what we call geological criticality. And if you look at, for example, lithium trade that we have as a result, in our model, you can observe that, for example, in 2050, a huge part of lithium will be produced in South America. And if you look at the dependency on the different regions regarding lithium, you can see, for example, on the right here, that for the same 2D, the US, India, China, but also in India, will be highly dependent on lithium for their energy transition. We look also at the copper copper because we consider that it is very important also to look at structural metals. And if you look, for example, at the material intensity of the low carbon technology, for example, here on the left, you can see the copper content for different type of vehicles. You can see that, for example, for a passenger car, the small size of passenger car vehicle, each vehicle will have 20 kilo of copper per vehicle. But if you go to pure electric vehicle, the same for the same size, I mean small size, you will have around 80 kilo of copper per vehicle. So it means that material intensity, for example, for transportation is higher for low carbon technologies than for traditional technology. And if you look at the electric, at the power sector, you will observe exactly the same thing. I mean, here is the copper content per megawatt installed. And you can see that, for example, for solar, for wind, you will have much more copper contents per ton per megawatts than for traditional electric generation, I mean nuclear or gas, etc., etc. And in the case of copper, when you assess the same kind of geological criticality, you can see that from 2005 to 2050, we will consume around 90% of the global copper resources. And this is the materials which can be considered as the most critical in our study. It means that we should have problem, you know, for copper, because copper is widely used in electric, in power sector, but also in automotive sector. But for sure, you can, with this kind of model, you can also assess different kind of public policy, you know, in order to reduce criticality. And for example, if you switch from business as usual to sustainable mobility, you can see that on this graph that you can avoid a certain amount of consumption. And it is exactly the same thing with recycling, because we put also recycling in our model, and recycling can help, you know, for reducing the criticality of the different materials. If we go now to cobalt, this is exactly the same kind of graph. If you look at the cumulative demand reported to global cobalt resources in percentage, you can see that cobalt in 2050 will be also highly critical, because we will consume around 83% of the global resources. How to reduce criticality? For cobalt, one option, for example, it's to change as kind of batteries that we use in automotive sector. And we have also modeled different kind of batteries, you know, a high cobalt content battery, a middle one, and a small one. And the fact is that you can reduce the criticality from 83% to 64%, depending on the kind of batteries that you use. If you go to nickel, geological criticality is around 61%. And if you look at bauxite, which is widely used, you know, to produce aluminium, the geological criticality is around 87%. So what can we conclude? All the scenarios that we develop in this presentation or in this article tend to show that the energy transition dynamic could lead to a decrease, and a huge decrease in the metal safety margin in a 2-degree scenario. I mean, the most constrained scenario, with a business as usual mobility. And what is also very interesting, it is the fact that if you compare what we call structural metals and strategic metals. Well, if you look at newspaper, everybody is talking about lithium, everybody is talking about rare earth. And if you look at the result that we have regarding these different scenarios, you can see that the most critical metals regarding the energy transition will be first copper, and second it will be bauxite. After that, for sure, cobalt will be critical. Nickel is a little bit critical too, but lithium and rare earth, there is no geological problem related to their consumption or their production from now to 2050. And you know, now we have a very famous quotation, you know, when we are doing a presentation, where we are always saying that small metals, small problem, big metals, big problems. And the fact is that we consider that public policy should focus on structural metals first, because they are widely used, you know, in different sectors and not only in automotive or power sector. I did not have time, you know, to add stuff related to economic, industrial, geopolitical, or environmental, but for sure they are all these different fields need to be questioned. And more especially, if I take the case of lithium, for sure we do not have a geological criticality, but when you look at the organization of the market, I mean the fact that five companies, they represent around 90% of the global market share. You can think about the catalyzation of the market in the future year. What can we say also? It is the fact that public policy is a key issue for metals regarding the energy transition. Sustainable mobility can help, you know, to reduce by around 2% the quantity of copper that will be consumed globally for the automotive transport. But for all the metals that we have worked with, having a sustainable mobility is a key, you know, to reduce the criticality issue. What about the next step? And I will finish my presentation. We will redo different scenarios with, it won't be a 4-degree or 2-degree scenario, it will be a carbon neutral scenario. And we are currently working also on the material contents of hydrogen technologies. And more especially, we are focusing on the water content of the low carbon technologies. So thank you for your attention. And if you have any question, I'm here to answer them. Thank you.
Thank you very much, Emmanuel. Thank you for this very interesting presentation and the perfect time you used to present your results. So that's great.
I rush a little bit.
Yeah, for sure, but that's the game. Okay, so if in the audience there is some questions, feel free to write it in the discussion panel. From my part, I have a small one. Yeah. You mentioned it briefly at the end of your presentation, but you demonstrate that they will have risk on or criticality. Criticality, thank you, on copper and bauxite and aluminum, of course.
Yes.
In your calculation, which level of recycling you used concerning maybe copper and aluminum and bauxite and aluminum for that case, but also for the other one, is it some quite high level of recycling of low level, and did you include this recycled material directly in the same industrial process?
To answer your question, first of all, we did not implement recycling, for example, for lithium. We started to implement recycling for copper, And for copper, what we did is the problem with recycling. First of all, it is not a panacea. What I mean is that if you look at the different sector using, for example, copper, you will see that you will have a different level of recycling. If you look at, for example, construction, if you look at infrastructure, you will have recycling around 55 to 60%. If you look at consuming goods, you will have recycling around 30 to 35. So it means that we took recycling numbers depending on the sector, and we put the recycling number that we have now. And we also implementing a possibility, you know, for the system to increase the level of recycling.
Okay, thank you. That's clear. I know no more question in the discussion, so I have another one. You talk also briefly at the end about the geopolitical aspect of this availability of this material. Did you identify in your study and your works some main issue concerning one of these materials for potential geopolitical risk, as easy as we can imagine for the next future for sure?
On each market, you have a geopolitical content and maybe a future problem. But the main one will be that if you have some kind of red line that you can that you can observe when you work on these different commodities. This is the fact that for I think 90% of the commodity, and more especially commodity for energy transition, China is refining around 50 to 60% of the different metals. And the fact is that there will be a huge concentration, for example, for copper, but also for lithium. I do not speak about rare earth, because it is well known that China is producing around 60% and is refining around 80 to 85% of the rare earth. So the main problem will be I don't know if it is a problem. The fact is that there is a huge industrial concentration of the refining chain in China, and this is a problem.
Yes, yes, absolutely. You're absolutely right. Okay, so from my side, no more interesting questions. So as I don't see any new other question in the discussion field.
I'm sorry.
Sorry.
I think there's a hand that is raised.
Yes.
I don't know.
Sorry, I don't see anything on the screen.
Okay,
so.
I will let you know. Yeah, please
yes.
Laurent.
Yes. Hello.
Hello.
Yeah.
Can you hear me?
Good.
Yes.
Okay. Yes. Thank you. So thank you very much for this very interesting presentation. I had one question regarding given the high, let's say, high energy intensity of minerals extraction and then refining and then the manufacturing parts. Did you imagine maybe a feedback loop or something like that regarding those metals to check whether the very intense use of these metals, especially for the 2 degrees scenario, is still in rail for the, let's say, the 2 degrees scenario, that you don't have like a feedback loop that produces a lot of CO2 emissions due to the very high mineral consumption.
I don't know if I understand correctly your question, but if it is a, what do you mean exactly? Do you mean the fact that there is a very intensive material production or refining? they could have a higher emission in the system. This is what we want to say. But this is included, this is included in the model, because yes, each time we implement a supply chain, for metals, we consider all the, our refining processes, but also production processes. So it means that it is included. It is included in the system. Otherwise, it's not possible, to limit the system beyond 2 degrees or 4 degrees. So we have considered all the emission also of the conversion processes of the materials.
Okay, thank you. Thank you very much.
Thank you to everyone. I think we have to switch to the next presentation. So thank you again, Emmanuel.
Thank you.
For the second presentation, we will have a presentation from Etienne Sorin from the EDF R&D department. Etienne is a research engineer as I mentioned before, at the EDF R&D department in the Economic Operation and Study of Energy System in Paris. His research interests are mainly storage, economic, electricity market, and ancillary services market design. He holds an engineering degree for the École Polytechnique, Paris, and as well a Master of Science in Sustainable Energy and Electricity Market from DTU Copenhagen in Denmark. So the presentation will concern an alternative approach to analyze competitiveness between storage technology using LCOS. Please, Etienne, the floor is yours. You have 20 minutes.
Thank you. I cannot share my screen right now because, Emmanuel, you're still sharing your screen.
Maybe you have to... Is it possible to switch off the sharing?
You have to share it. So down, normally there is where in the écran partagé icon, you can unclick it.
Yes, but I think, okay, Emmanuel. I can.
Is it okay?
No, I think it's Emmanuel. Yes.
Great.
That's good.
Perfect.
Okay.
Yes, it should have been Emmanuel. Yes. Perfect.
Etienne, you can now share your screen, I think.
Okay.
Good.
Can you see the screen?
Yeah, that's better.
Thank you, Bernard, for the introduction. Hello, everyone. For those of you who were there at the keynote session early this afternoon, there was a question for Paul Roscoff from MIT that stated, that was the last question, that was about storage technologies, and the question was which storage technology is going to win the market in the future, which is going to be the dominant technology. So that's quite a vast question, and that's a bit my presentation is a part of the answer, a small part of the answer. And the answer relies on many factors, and the first of it is to define the need for flexibility that drives the penetration of storage. So we have an increasing, that's quite standard, increasing penetration of renewables that requires increasing need of flexibility on the electric system to match at all time the load and the renewable generation. And that's a critical aspect of what's going to drive the technologies that are going to win the market in terms of storage penetration. Because if we look at the technologies, we have several technologies, potential technologies that could answer to the flexibility need of the system. One way to compare them, the first way is a technological way. We have on the axis, we compare the technology depending on how dynamic they are and how much energy they can store and during how long they can store the energy. So it's the two dimensions represented as one. So we have several technologies. The most known are hydro storage, so the pumped hydro storage here, PHS, the lithium-ion batteries, of which we talked a lot today in general, that can deliver very dynamic flexibility and but also some hourly products. We have also some other storage, for example, flywheels that are dedicated to very dynamic products. Some are more lengthy storage with compressed air energy storage, and others for long-term storage with hydrogen and heat and cold storage. Of course, all of the technologies are not here, but it's just a first overview of the technologies and a way to compare them. Then to match these technologies, we have different systems that are required to operate the different services that are required to operate the system. They can also be compared in terms of how dynamic the product is, or how much energy is required to provide this service. And we can see that there is a whole range of services that corresponds to the whole range of power and energy technologies, storage technologies that we have. So you have most of them are well known. So you have all the energy shifting at the bottom. You have some peak shaving here that are some hourly products, but depending on the application can also be a bit longer. And you have some very dynamic applications such as frequency regulation. Of course, all these services, they will the way to provide these services will depend on a country by country basis, on the electricity mix and so on. Then, if we want to go a bit further into comparing storage technologies, we need to look at economic and technical indicators. Usually, the first one that we use is maybe the capex. So usually the annuity of capex that gives us a first overview of the cost of a technology of a storage technology. And then if we want to go a bit deeper, usually the next indicator that comes to mind is the LCOS. So LCOS is for levelized cost of storage. And usually a good way to introduce it is to compare it to the LCOE. That is the levelized cost of electricity that is usually used to compare generation assets. So the LCOE will give us the average price at which the electricity generated by an asset needs to be sold in order to even all the costs that are needed to build the asset and to operate it over the whole lifetime. For the LCOS, it's exactly the same. So there is the LCOS assumes that the storage will be something similar to a generation asset, and we'll compare depending on how much the storage asset has injected onto the grid over its lifetime. What is the average price at which this electricity needs to be sold in order to compensate all the costs of the storage? But on the difference to the LCOE, the storage technology is a bit more complicated because if we inject into the grid, we also need to withdraw electricity from the grid. So we need to include also some costs related to that. So in the cost definition here, we have capex, opex, and so on, and then we have another term that takes into account all the recharge costs. So there are this formula is here. It's very simplified. In the literature, when we look at the formulas that are provided for LCOS, there are lots of parameters that are included to provide very detailed estimation of the cost that supports technology. We could include parameters such as self-discharge for technology, also some financial aspects such as inflation or taxes with amortization and so on. So there is a bit of competition in the literature to which extent we can have the most defined cost structure, to have the most detailed cost structure for the LCOS. But the thing is, when we look at the LCOS, we often talk about costs, but we forget about the other part for storage, that is the application. If we build a storage technology for a given service, that means that it's going to be operated in a certain way. At the difference of renewable assets, for the renewable assets, once it's built, it's going to generate electricity, and the generation of this electricity does not depend on anything else than the solar or wind generation profiles. So there is no specific operation from a human part. We could think of operation and maintenance and so on, but there is no big decision that needs to be made to choose when to produce and so on. For a storage asset, it's a bit different because we can choose when to charge, we can choose when to discharge. So the approach needs to be a bit different. So the comparison between the LCOE and the LCOS needs to end a bit at this point. So we need to have a description of how the storage technology is going to be operated. That's the key assumptions that we need to provide here that are in the square. So you have some yearly cycles that the storage is going to provide. You have some cost for the storage. So it's usually just an average price over the year. So if we have some cycles, we need to recharge a given amount of electricity, and this amount is priced at a given price in euro per megawatt hour. And then we also have another key assumption that we need, that is the storage duration. It's a two-dimension problem. For the LCOE, we can express it in per megawatt installed capacity, but for the storage, we need also the energy aspect of capex. It's a critical aspect for capex, but it's also a critical aspect for the use case. Because if we have for example, if we have a lithium-ion battery that is required for long-term storage, for let's say weekly storage, for example, we will need to have more installed capacity. Then once we have these assumptions, we can build this kind of graphs. That's a very simplified one that we could build. So we have three technologies, each with their capex, their efficiency, and so on. And we're going to operate it in a fixed way, which is we're going to charge them every day for 6 hours, and then discharge them all the energy charge during the same day. And then we vary in the x-axis the charging price to see what's the most cost-efficient technology to do this, depending on the price. So for example, in the low price area, if we are able to charge at a low price, then the technology 2 seems to be better. If on the other hand, we are in the high price area, then the technology 1 and 3 are better because the technology 2 is penalized by its low efficiency, so high losses. So that's a kind of graph than we can have. And then we can have some much bigger analysis of LCOS, where we can analyze for all possible services, so all possible number of yearly cycles and all possible storage duration, what would be the best technology to provide the service. So that's usually some answers that we can find in some papers, where we are going to vary the number of yearly cycles, the number of the storage duration, and then we check what is the most cost-efficient technology for each combination of storage duration and number of yearly cycles. And the rationale behind this is that to each combination of these two parameters, we can match a real-life service. So, for example, FCR, so frequency regulation services, so the primary regulation, we're going to have a storage duration of 1 hour usually, and a number of yearly cycles of 300 and around 300. So it's usually around 1 cycle per day. So that's, if you take these two parameters, then you get LCOS comparison for FCR. That's the usual approach. The thing is, these assumptions, if we have fixed assumptions like this, then we only have a partial view of the competition between storage technologies. The point of view is that if we have a fixed number of cycles per year and a fixed storage duration for all technologies, it means that the service that we need to provide is very detailed. So it usually matches a PPA that where the requirements in terms of injected electricity or in terms of withdrawn electricity are very well defined and are the criteria on which the technologies are compared. But if we go for more market exposed assets, then if we look at how the storage technologies are driven, then we see that there are some other parameters that needs to be taken into account to understand how much a technology will be operated, how much it will cycle, and what is the optimal size required. Some of these parameters are listed here, so round trip efficiency, the aging, the self-discharge, and so on. And so we need to take all these parameters into account and have some kind of optimal dispatch, depending on the services that needs to be provided, to find the optimal sizes, the optimal dispatch of the technology, which means that it's not possible to have a fixed assumption to compare all technologies. So that's the first point. If we want to look at examples of why it's not true to have these fixed assumptions, the first one is to look at wholesale arbitrage. So that's the most common services that is usually mentioned for storage, in which we buy electricity on the wholesale market at a cheap price and sell it at the highest price possible. Here we simulated an optimal dispatch of different storage technologies depending on the round trip efficiency on several price series from historical price series. And then we check what is the optimal number of cycles per year on which the technology is to be operated. And we see that the round trip efficiency has a huge impact on the number of cycles that a technology will be operated on. For example, technologies with very high efficiency, they have very low losses, so they will need a very low spread of prices to cover the losses. Whereas technologies with low round trip efficiency, they need very high spreads to cover the losses. So they will be cycling very infrequently, because it's quite rare to have this kind of spreads. So if we look at this in terms of so the number of cycles is affected, which means also that in the end, the LCOS of this service from a market exposed perspective will be also affected. The second example is for FCR, so the service I was mentioning just before, frequency containment reserve. If we look at pumped hydro storage, the optimal approach to look at FCR for pumped hydro storage is to not take too much into account the energy sizing, because it's not impacted by the service, but rather by exogenous factor. And the power sizing of the asset is also independent to the energy sizing. For lithium-ion batteries, on the opposite, the power and energy sizings needs to be thought as a combined process of optimization, and we need also to think of a continuous recharge strategy that also will bear a cost on the technology. So we can see that to provide the same services, there is not the same question that we need to ask ourselves to find the optimal product, the optimal sizing, and the optimal dispatch of a given technologies to provide this service. The second point that could be a second limit to the LCOS when looking at market exposed assets is that in practice, if we look at the storage assets that are developed today, they are mostly on a multi-service approach. So here is a simple example of a multi-service approach. Here it's one that is very common in Germany, where the peak shaving is a quite remunerating service. So we have lots of lithium-ion batteries that are built to provide peak shaving for example, for industrial consumer or for residential consumer. And the fact is that providing these peak shaving services only impacts on a very limited number of hours. So maybe 10% of the hours of a year will be used for peak shaving. And if we don't use the battery for the rest of the year, it's a stranded asset, and we will lose opportunity to have a better remuneration. So what we do usually is that the time when the battery is not used for peak shaving, so here is the area in pink, we will use it for FCR. So usually the batteries that are sized for peak shaving have a sufficient sizing for FCR. So it's an asset that we can use for it, and it's probably the best one that we can use it for in the time that we have. That's an approach. Another approach that we had is one in the European project called EU-CIS Flex that analyzes the provision of flexibility on the European grid with different systems. One of them is a VPP. It's a VPP of renewable sources of generation and a battery. And in this example, the VPP is providing some FCR as well as some spot optimization. So it optimizes at the same time the selling of electricity on the spot market, so the electricity generated by the renewable sources, and at the same time providing some FCR. And you can see in the bottom the dispatch of the VPP in red, and at the same time the dispatch of the battery in black that helps the VPP to provide these services. So here it's a very different example of a multi-service approach, and it shows us that using a LCOS formula to describe this kind of storage development is not going to give us a very detailed vision. If we want to summarize it, a multi-service approach can be represented in this way. Over the lifetime of the technology, we need to cover some costs that are every year that are represented by the square in the dotted square in black. And over the lifetime of the technology, the storage asset will provide different services sometimes at the same time, but also sometimes sequentially in terms of hours, in terms of year, during the lifetime of the asset. The LCOS formula, on the other hand, looks at only one services and will assume that the service provided to the system is usually the same over the whole life. So we can see that the LCOS formula usually will not give us a good overview of practical storage assets, but the question is, when do we use it if not for practical reason? That's my conclusion is to I see that I'm at the end of the time, to see in which cases the LCOS can still be used, if not for practical aspects. So to summarize, the LCOS is still an interesting indicator because it brings down all the cost structure of a storage asset into something that everybody can understand. So your price in Europe per megawatt hour is something we can feel, and it's a good approach to having a understandable comparison between storage technologies. We have the same critics as the LCOE, which means that we don't have a full picture of how the storage is inserted into the grid, what it provides, and so on. We had the same critics for LCOE for renewables. We don't take into account for LCOE However, this indicator of if we look at a use case by use case approach, if we have dedicated method for each use case and each technology, then we can have a good comparison of these technologies for a given project. So for microeconomic analysis. So we can still use it in this case, and that's when it's mostly used by manufacturers storage technologies. Okay, they have some projects for which they are required to provide some batteries, for example, and they will communicate on their US, but not to compare across various technologies and various use cases. So with that in mind, the LCOS should be used. It can be used to drive policies and to communicate on the competition between storage technologies, but it should be used with caution because it doesn't provide the whole story. And finally, it gives a distorted view of the competitiveness of market exposed assets. As I was just saying, we don't have with the LCOS a complete view of what is required for storage technologies to be operated. Thank you. And if you have questions, don't hesitate.
Thank you very much, Etienne. Very, very interesting presentation, and just on time, more or less, so that's good. So I saw that there is a hand, there is a question from Filippo Beltrami.
Yeah. Hello, thank you, everybody. Thanks for the presentation. And funny enough, I was the one asking about the question during the keynote session about the comparison of the technology of the storage technology.
It's good that you're here.
Yeah, it's incidentally I'm here. So I just have a couple of questions, and you with this presentation you replied to my question during the keynote one. I'm just wondering when you calculate the levelized cost of storage, what do you include in as a practical question? What do you include in the recharge cost at the numerator? Do you include the cost of buying energy for storage plants? So basically the day-ahead prices. And the second question is that, are your simulations adapted to practical, actual power plants, or is modelization based on the coefficient, some assumed coefficients about efficiency, and yeah, some assumed parameters? I don't know if I was able to phrase it correctly. So, but anyway, congrats for the presentation again.
Thank you. So here I have the formula that it's not the most complicated that we could use, but it's one of the formula that you can have for LCOS. So you have the capex, and then you have the annual cost revenue streams. So you have some OPEXs, and then you have the cost to buy electricity. So you have a given volume of electricity that you discharge on the grid to provide the service. So that's the V parameter. And to calculate how much you need to charge, then you divide this V by the round trip efficiency, or rho, and you multiply by the price, lambda, for the average price for the given year.
So it's
yes.
an average price from the negotiations of the day-ahead market.
Yeah, it all depends in the end on how you're looking at the charge. It could be the average wholesale price that you had, but it also could be the perceived average wholesale price if you have a more detailed approach to the LCOS. And that's usually what we do when we calculate LCOS for use case by use case application, is that we optimize the dispatch of the storage technology. Then from the optimal dispatch, we can deduce the average charging price in practice. And that's the one we're going to use for this formula. Yeah.
Thank you.
And for the second part, so I'm not sure if the formula explains it, but also if I understood correctly the question, you were asking if in practice for the system view of the storage we use the efficiency, right? Yes.
Yes.
Yes. So yeah, it's true. We need to take it into account at various aspects of the revenue streams. So you have of course the charging here, where you take into account the efficiency, but you also need to take it into account in terms of as I showed in the presentation, in terms of cycling. The efficiency will affect a lot the cycling, because you need to cover the efficiency losses to be beneficial. And that's for wholesale arbitrage, but for other application as well. If you look at for example FCR, doing FCR, you will have a lot more energy to recharge if you have a low efficiency, because you have more losses.
Nice. Thanks a lot.
Okay.
Thank you. Is there another question, or in that case, I have a short one, and if you can answer briefly, do you took in account in your calculation just for the stationary battery available for this kind of activity, or are you able also to take in account some other type of battery, maybe not for the moment, but for the future, like battery in the vehicles and can be linked to the grid and be able to share energy or power, etc. And do you think there is it could be have an impact on this calculation and result in terms of capex, opex, or I don't know what?
Yeah, totally. We don't calculate LCOS yet of electric vehicles. The question behind that is usually that it's the same as for the multi-service approach. When you have multiple services, you don't know exactly how to share the cost of the storage between the different services.
Yeah.
So if you have electric vehicle, then usually what we will say that is that the whole cost of the battery is paid for already, and everything that we do with the electric vehicle is just some bonus. So usually for that, it would mean that we would have capexes close to zero, or some capexes if you need to invest in a V2G recharging station, for example. So you just include the capex for this. And on the other hand, the OPEX and the recharging costs, you need to think of them just as the OPEX and recharging costs specific to the application that you're providing. So if you have recharging costs for the electric vehicle just for driving, then those should not be taken into account in the formula. So usually, if we look in terms of LCOS at which cost an electric vehicle can provide a service, we don't have the numbers yet, but you should find that it's at a much lower cost than lithium-ion batteries because the share of the cost that they need to compensate is much.
Thank you very much. Okay, so thank you very much again, and we will switch to the third presentation.
Thank you.
So thank you. Can you turn off your sharing just to be sure that Enrique can take the lead. So now we will have a presentation from Enrique Cristobal. Enrique has a training with a degree in economics, and other formation on master in economics and finance, and it was finished by a doctorate in economics and business from the University of Navarra in Madrid. During the last few years, he focused on topics on issues on energy economy, energy transformation, and climate change, applying advanced econometric techniques for time frequency analysis or fractional integration and co-integration techniques. Actually, for the moment, currently, is associate professor at the University of Navarra and UNIT Business School, also in Madrid, Spain. And he will present us a paper named Merger and Acquisition in the Lithium Industry, a fractional integration analysis. Please, Enrique, the floor is yours.
Yeah, thank you. Thank you for coming, everyone. So let me share my screen. Okay.
Good. Perfect.
It's okay, right?
Yeah, you can go.
Okay. So let's see. Okay. So thank you very much for coming and for your extensive presentation about me. So the paper I'm going to present today is Mergers and Acquisition in the Lithium Industry, Fractional Integration Analysis. As you mentioned in my presentation, we basically apply high econometrical methodologies to analyze the trends in some series, and especially in this paper, we try to see how these merger and acquisitions in the lithium industry, as the first speaker said, are very common in this sector. We want to see, especially here, how the trend in these mergers and acquisitions is developing during the years and how we expect this series behavior in the future. Okay, so this is about me. You mentioned before. So the main outline for today, I will make a brief introduction because probably the other speakers talk about lithium more than me, so it's not necessary to make it big. So later we will talk about the data we use in this econometrical paper. It's an empirical research
Later, the methodology we use, in this case, low memory methods and a fractional integration analysis.
Sorry, I think there is a mistake with the screen is frozen. So do you change your slides or you are still on the first page? Maybe there is a problem of double screen.
The problem, I think, is that you are on a PDF, and in a PDF you just have to scroll down.
I can change it.
Okay, we've got the outline now. That's good.
Yeah. I think this is fine, right?
Yeah, that's fine. Thank you.
So as I mentioned, first I will introduce the topic, but as I said, the other speakers talk about lithium also, so it is necessary to cover it a lot. We will mention the data we use to develop this empirical research paper. The methodology, as I mentioned before, we will apply econometrical methods based on long memory and fractional integration. And we'll cover the result and the main conclusions to these merger and acquisitions in lithium industry. So about the introduction, obviously during the last years, the concern about mineral resources has increased a lot. The other speakers talk about this, and basically because obviously we are changing to climate concerns, and lithium has a strategic role in this sense, as it is used in manufacturing a lot of electrical devices, especially to the car industry. As you also mentioned in another presentation, rechargeable lithium-ion batteries are basically made by lithium. So
I'm sorry, Enrique. We are still on the outline slide.
Oh my God.
Yeah. I think
yes, I'm sorry. It's still not scrolling.
I'm gonna try again. You see the introduction now?
No, it's still outline.
No, it's still on the outline.
Let me.
We saw
maybe
your
just unshare, and then once you unshare.
No, I'm gonna. Let me just do this.
If you
now you see.
Yeah,
the screen?
that works too.
Yeah.
It
works.
It works much better. Yeah.
Okay.
Thank you.
Yeah. As I said before, only like a little motivation of the topic. The concerns about mineral resources has increased a lot during these years, basically because, as I mentioned, the development, for instance, of car industry, electric car industry, changed the demand of minerals like lithium, which is basically used to manufacture lithium-ion batteries. So this problem storage has increased the demand of lithium in this case. So we observe a lot of changes in the market, and one of that changes is that we observe an increasing trend in the number of mergers and acquisitions in this market. So we observe a concentration of companies in this sector, and it's a thing that was mentioned by the first speaker. I think he said that 5 companies in the market covers 90% of the mineral market. So it is a very high concentration in this kind of markets. So we are interested in analyze this trend in the future with this paper. Obviously, petroleum is losing importance, especially in transport, and it is expected to change to electric car in more or less 10 to 25 years. Okay, so this will increase the pressure in the mineral resources that are used to manufacture clean technologies. Okay, so here in the graph, just to the motivation, you see in 2013 how the percentage of the global lithium markets for batteries. In this case, you see the chain of the trend, and this obviously affects to the concentration in the market. And that's what we will analyze with the data. So about the literature review, obviously authors like Gord and Coase argue that economic and industry shock produce reallocation through merger and acquisition. So it is tested that in the economic industry in general, when we have this economic shock, like for instance changing for clean technologies, this will produce reallocation into merger and acquisitions. And we also observe that all companies located in China and Saudi Arabia are investing in renewable energy sources through merit and acquisition. And this is because they are not experts in this market. So basically, they enter into the market, they try to participate into the market through this merit and acquisition. So the petrol industry is coming into the lithium industry through merit and acquisition because they don't have exactly the knowledge, and we see that in the data, okay? And other authors also affirm that merit acquisitions create some efficiency gains. There are other authors that are exactly against this statement, but this is only an opinion. And obviously, these mergers and acquisitions carry variable and fundamental information about the future trend of the market. And this is why we are interested in analyzing from an econometrical point of view this trend of the series, because we think that if we see the trend of the mergers and acquisitions, we can predict the behavior of this market in some sense. Okay. And again, Hartford in 2005, as we mentioned, economic, technological, and regulatory shocks provide the climate to merit and acquisition, and this is what is happening in the market, as we saw in the graph. So several papers dealing with these merit and acquisitions we saw in the first paragraph some of the main authors, but we are going to focus in the last three ones. This one and this one. First down in 1992 and recent 1999, use switching models to model this merge series. This is some models that are not the best ones, the ones we use right now, because obviously econometrics also advanced a lot right now. But more recently, some of my co-authors of this paper, precisely, Professor Monge and Gil-Alana in 2018, use methodologies based on continuous wireless transform and autoregressive models like bar models to study dynamics of the lithium industry and merit and acquisition. So basically, my co-authors in another paper studied this same series, but from using continuous wireless transform and autoregressive models, just to see we have exactly the same result. So now we are applying long memory methods and fractional integration just to check that the results that we made in other papers are exactly the same. So the last author, Boss et al. In 2018, again, provide a novel perspective to the oil market, examining merit and acquisition. In this case, not to the lithium industry, but to the West Texas Intermediate, which is the measure we usually use to observe the behavior in the oil market in this case. So particularly in this paper, we are going to analyze the influence of merit and acquisitions in the behavior of lithium sector, applying two methodologies, as I mentioned, long memory methods and fractional integration methods. And as far as we concern, no previous econometric works are studying this series related with lithium, applying this methodology. So that's the main contribution of the paper. About the data, we have this graph, and we can easily observe how mergers and acquisition increased a lot after the crisis in 2008. This obviously, when we have a crisis, obviously the big ones are the ones that covers the market, and they tend to concentrate even more, and that's why we observe an increasing trend in the mergers and acquisition, and the graph shows it very clearly. And well, about our data, this is monthly data from May 1985 to January 2019, obtained from Thomson Reuters Econ database. Okay, in principle, we have daily data, but we aggregate all the data monthly, basically because we consider changes in mergers and acquisition at a global scale are better observed by months, not by day. And we think it's a proper way to look at this data. Okay. About the methodology, I'm not going to go deep about the methodology because it's very complex, and it's the part where my colleagues Luis Alberico, Gil-Alana, and Professor Manuel Monge are the specialists in this kind of methodology, but again, techniques based on long memory and fractional integration. Okay, we will talk some right now. So basically what we are doing when we develop, for instance, an ARMA model, in this case, we corroborate two hypotheses between 0 and 1. Here we are adding the fractional integration approach. And for that, we need to estimate the parameter called D. And this is the main objective of the model, to estimate the parameter D. To estimate it, you use both parametric and semi-parametrical techniques. And the main criteria is as long as this is smaller than 0.1, while it is non-stationary for D more or equal to 0.5. That's the theory, the main theory of the model, just for you to understand the empirical results. And the criteria we're going to use is if D is smaller than 1, shocks in this series will have a transitory nature and their effects will disappear in the long run. Okay, so if the result we will show you in the model, the results of the D are smaller than 1, this will mean that this source will be transitory. This series will come to the same level in the long run. But if we have a D more or equal than 1, in this case, shocks are non-mean reverting and their effects will persist forever. So that's precisely the objective of the paper, to see if the data we have about meridian acquisitions in the market for the future is going to be the same, that effect, or we are going to revert this area and to come back to previous levels. Okay. So the results, these are the empirical results, the tables I want to share with you. I'm not going to go deep. The white now results are 0.36, and in an autocorrelation point of view, 0.59. And this is estimates of D based on semi-parametric methods. Remember, we use both parametric and semi-parametric methods. So these are the results for parametrics and for semi-parametric methods. So let's go to the main results and its interpretation. In a wide parametric approach, value of D is lower than 0.5. In fact, it's 0.36, as we see in the table, 0.36. So this means that the series is stationary in this case. If we impose autocorrelation in the series, okay, if we impose autocorrelation, as we see here, the result is 0.59. So in this case, transitory shocks, though long-lasting effects. So that's the main result. So first of all, the results based on this parametric approach, the first one we are going to do, produce some confronting results, because remember the criteria is results above and results over 0.5, and results are confronting. But under autocorrelation is apparently the more realistic approach. So the estimate value of D is much larger and above 0.5, implying in this case a non-stationary pattern. Okay, so from the parametric approach, we can say that we observe a non-stationary pattern for this series. Okay, and for table 3, remember, then semi-parametric point of view, we can say we observe that all of them are once more in the interval between 0 and 1, supporting fractional integration and also above 0.5, which implies basically non-stationary through mean reverting behavior. Okay, so with these results, the main conclusion of the paper is first, our results suggest that both series is fractionally integrated and mean reverting, as the estimated value of D is lower than 1. So for the first criteria, value in both cases is lower than 1, both for the white noise and imposing autocorrelation. Remember, the values were specifically 0.36 and 0.59. So in both cases are lower than 1, imposing autocorrelation and white noise. Nevertheless, it seems to be stationary and under the white noise. Okay, but non-stationary and under anti-correlated disturbances, which is basically the approach we choose in this case. And performing parametric approach, we also mentioned that this implies, the results implies transitory shocks with long-lasting effects. So basically, after this econometrical approach, the main conclusion for this series we analyze, remember, we are analyzing the quantity of mergers and acquisitions in the global market. So we can say that the impacts for the lithium industry will be transient and are expected to disappear on their own in the long term. In other words, these shocks in the market, the changes we are seeing in the market are not going to be fixed for the future, and we are expected to have the same levels in the long term. Possibly because the market cannot absorb more merger than acquisition. I mean, this is a big market, but not many companies are participating in the market right now. So obviously in the future, not many more merger than acquisitions can be carried out, and that's probably why our model is showing these conclusions. So that was basically the paper. So you have any question, please let me know.
Good. Thank you very much, Enrique. Very clear, and you go a little bit faster than the time you allowed, so we have much more time for discussion and for questions. Yeah. I don't see for the moment any hands, so I have a question just to be sure to have well understood your conclusion. You mean that for the lithium industry, we will have for the next year a kind of stability in terms of main actors involved in this industry, due to the fact that the merge and acquisition processes are, as you mentioned, accelerating, but with a lowest impact in the duration. Is it right?
Yeah, sure. Maybe you can see with the main graph. So the conclusion is here we see a very high trend in the number of merger and acquisitions, and the other speakers talk about that. Obviously, we have a crisis, and when we have a very rich market in general, obviously the big players try to concentrate in the market, and that's the trend we are observing in the data right now. But if we analyze the series from the beginning, from our econometrical point of view, the conclusion is that this effect is not gonna be long in the future. Okay, so right now, in the next 1, 2, 3 years, probably we will observe more mergers and acquisition, but in the long term, we will probably stabilize and come back again to the same numbers we observed before. That's the objective of the paper, and that's the conclusion we want to show with the study.
Okay, and in this decision, do you have an idea of the duration that you need to have this stabilization after the peak, for example, or something like that?
With these methods, we cannot offer that conclusion, but probably if we apply the methodology I mentioned before, the wider coherency methods, in that case, we can talk about the duration of the effect, and this could be another future research area to evaluate with wireless coherency methods exactly the quantity of months or years this is going to last, and we can do it, and we will provide you it in a near research paper.
Okay, thank you. And then another question: we observe in your curve that you mentioned that there is a first, not peak, but the first change due to the economic crisis. The second one, do you have an analysis of this? Yes, in this location. And yes. After, my question is, do you think that with the crisis that we observe more than 1 year now for the sanitary crisis, do you think that it could have an impact on this type of merger and acquisition, not only on lithium, but on general industries?
Well, I think here we have two answers. I think that first, when we hear the word crisis, in almost all sectors, we are going to see these merger and acquisitions. So some part of the explanation would be that. But in this case, the main explanation for this movement in the curve is the increase in the demand. I mean, the electric cars are increasing a lot, so the demand for ion batteries is increasing, the demand to lithium is increasing. So once we increase the demand, we are increasing the size of the market. And when we increase the size of the market, this is, I mean, more attractive for big companies to do mergers and acquisitions. So I think the main explanation would be that, I mean, the demand for electric cars is increasing a lot, so we need more lithium, the demand is increasing in the market. But obviously, if we add the component of the crisis, only for the world crisis, this always lead to a concentration in the market, and this will be also an explanation for sure.
Okay, yes, I think for the increasing of electric vehicle demand, I think it's something to be sure to secure the amount of available, in that case, lithium for their own production or for the whole production. Okay, if I well understood. Okay, good, interesting. Yes, we've got another question from Filippo Beltrami.
Yeah, thank you. Only if I have time. I mean.
Yeah, you've got. Yeah, we have got a few minutes. Yeah,
I was short, so we have time. Thank you.
Okay, great. Now, I just have a couple of questions because the topic is pretty interesting. I was wondering, firstly, if you are planning for future research to relate this analysis with the behavior of prices of the raw material, so of lithium. I mean, the effect of merger acquisitions, probably possibly in the long term in terms of effect on the prices. And the second question is about the econometric part. Did you also try to use the standard unit root and stationarity tests to check the evidence of fractional integration for your time series variables? Because what I've learned from what I basically did last year was that this thing that unit root tests say something and the stationarity tests say the opposite. So that is also another explanation of fractional integration for your time series variables. And that's all from my side. Thanks and congrats.
Yeah, for sure, in another studies, we can also use unit root methods or specifically we focus on that. So, I mean, this is the first paper we developed focusing on this data, but as I mentioned, our objective is to analyze this data with another methodologies, including the wireless coherency, because we think specifically that is gonna offer us the long effect. We can measure the long effect, but obviously the unit root methods can be also added to the study for sure.
Thank you. So if we have no more questions, I thank you again, Enrique, for this presentation.
Thank you very much for listening.
Thank you. And we will switch to the fourth and last one. The presentation will be made by Marina Siebenhofer. I hope that I well pronounce your name. If there is a mistake, feel free to correct me, clearly. Marina. Good. Marina is a project assistant and a PhD candidate at the Energy Economic Group at the Vienna University of Technology. Prior, she works as a research assistant at the research unit for transport system planning, also in the University of Technology of Wien. And she completed a degree on spatial planning, also in the same university. His research work are main focus on energy policy in transport. She is coordinating also project proposal and involved in lecture at the EEG. Marina will present us a paper. Maybe Enrique, if you can switch off your. Thank you. Marina will present us a paper focused on successful policies to promote the dissemination of battery electrical vehicle, which is a huge problem. So please, Marina, the floor is yours, and you've got the same time at the other, of course.
Thank you for the introduction.
Good.
So I think you see my slides.
Very well. Thank you.
Yes. Okay, just a moment. Okay. Good afternoon or evening. My name is Marina Stunhofer. Yes, and I'm going to talk about successful policies to promote the dissemination of battery electric vehicles today. Okay, I have a problem with my the buttons. Just a moment. Okay. Okay, I'm going to divide this talk into 6 parts. First of all, I will give you an introduction about about why BEF should be promoted, followed with the core objectives of our study. Then I will give you an outline about energy policies in transport and incentives to promote BEFs. Next part is the methodology, followed by the results. Finally, I will end with the conclusion. As part of the European Green Deal, the Commission proposed to raise the 2030 greenhouse gas emissions reduction target to at least 55% compared to 1990. By 2050, climate neutrality should be reached. The transport sector causes around 30% of the CO2 emissions in the EU. Thereof, 72% is road transport. In contrast to other sectors, such as energy, industry, or residential, traffic emissions have been increasing rapidly since 1990. The figure on the right side shows the development of CO2 emissions in the transport sector, including road, railway, and aviation, for selected EU countries over the period of 1990 to 2018 in relation to 1990. In most of the countries, emissions had been continuously increasing until 2007. After a financial crisis, emissions decreased in most of the countries. However, this decrease was followed by an emission increasing trend starting from about 2013. Significant differences among countries could also be seen due to the country-specific circumstances, such as gross domestic product and national policy framework. If the number of conventional vehicles with internal combustion engines could be sharply reduced, the emissions from the transport sector would decrease. In the best case, EVs could cause 75% to 90% lower GHG emissions than ECEs. In contrast to ECEs, EVs, especially battery electric vehicles and fuel cell vehicles, have zero emissions at the point of use. The highest BEV market share can be found in Norway. 46% of the vehicles are there BEVs, followed by the Netherlands with a BEV market share of 15%. Far-reaching arguments against switching to EVs are high investment costs compared to ECEs and technical limitations. For example, limited driving range and charging infrastructure availability. The investment costs of an EV are about 1/3 higher in comparison to an ECE. To address the problem of the high costs, BEVs can promoted by the introduction of energy policies in transport. Core objective of this study is, on the one hand, an investigation of current economic state of the BEVs in comparison to ECEs by the calculation of the total cost of ownership, called TCO, for the major BEV markets, China, California, and the most important European countries, Austria, Germany, the Netherlands, and Norway. The countries were selected based on their EV market share and the amount of BEV sales. On the other hand, an identification of proper policies to overcome the high investment costs is given. This figure shows 4 dimensions which are fundamental for energy policies, for energy policy interventions in transport. The promotion of BEVs can be affected in the following ways: financial, through subsidies on the purchase price, or subsidies on the vehicle insurance or private charging infrastructure, or through exemptions from taxes such as the car purchase or registration taxes. BEVs can be affected regulatory through standards on the maximum energy consumption or CO2 regulations. Moreover, legal frameworks such as free parking for BEVs or emission-free zones can be introduced. Yeah. The next 2 slides shows the methods of approach to compare the economic performance of an ECE with a BEV. As already said, total cost of ownership was calculated. With the calculation of a TCO, direct and indirect mobility costs are shown from an individual perspective. The aim of the calculation was to identify the difference between the costs, considering the capital costs, operating and maintenance costs, and also the electricity and fuel costs. The TCO in euro per year was calculated as follows. The formula 1 is the TCO is equal to the costs of the capital for a vehicle plus the costs of operating and maintenance plus the costs of the energy. Formula 2 is the costs of capital is equal to the initial investment costs, including any subsidies and the capital recovery factor. The formula 3 alpha describes the ratio of a constant annuity to the present value of this annuities received for a given time. It is calculated using an interest rate of 5% and a depreciation period of 8 years. The formula 4 is the cost of energy depends on the price for the fuel or the electricity and the kilometer driven per year. We assumed 12,500 kilometers and the fuel intensity. Yeah. And the last formula 5 is the fuel price. Is the sum of the net price, the value added tax to the CO2-based tax and an excise tax on fuels. So in the following, we applied this method to calculate TCO for 2 specific cases. For small cars, we compared the costs of a VW Golf and the VW e-Golf. For large cars, we analyzed the costs for an Audi A5 with the Tesla Model 3. We compared the TCO for countries with some relevance of BEVs. For the EU countries, Austria, Germany, Netherlands, Norway, and furthermore China and California. Moreover, we calculated a sensitivity analysis with a change of the interest rate and the depreciation time. Let's move on to the results. On the left side, you can see the TCO results for the smaller. On the right side, for the bigger cars, differences in the purchase price of the cars within the cases are obvious, but comparability is given because of similar size and similar engine power of the cars. The lowest costs for BEVs are, as you can see, in the US and China, also in the Netherlands. The highest costs for BEVs are in Norway, Germany, and the USA. In the USA, the high costs for the Tesla Model 3 was only because Tesla was exempted from subsidies. Lowest prices for ECEs are in the US, highest in the Netherlands, Norway, and Austria. In the following, I will give you a deeper insight into the results, for example, Norway. Norway has the largest BEV market share worldwide, with 46% in 2020. Nevertheless, the annual costs for a BEV are very high. On the other hand, ECEs are much more expensive than in the other countries considered. This is due to the very high registration taxes and high gasoline prices. The costs of electricity, on the contrary, are very low. There are no subsidies for BEVs granted. However, it balanced itself out again. Nowhere else are so many monetary measures granted to BEVs as in Norway. The wheat, 25% is for the EU average with 21% rate high. As a result, the VW e-Golf is 1,000 euro cheaper than the VW Golf. The Netherlands has the largest BEV market share, the second largest BEV market share worldwide, with 10% in 2020. BEV costs are in the midfield and high subsidies for BEVs are granted. Just as in Norway, ECEs are very expensive. This is due to the very high registration taxes and high fuel prices. Similar to Norway, the e-Golf is 1,000 euro cheaper than the VW Golf. As a contrary example, I would like to show the results from California. The USA had a unique position in terms of the costs of ECEs. The prices are much lower than in the other selected countries due to the very low wheat of 8.25%. Additionally, there are no ownership taxes and on ECEs, yes. Furthermore, the gasoline price is the lowest within the selected countries, and high subsidies for BEVs are granted with around 5,500 euro per vehicle. This is the second highest value within the compared countries. In the USA, very few non-monetary measures were provided for BEVs. And the result is that the VW Golf is a little cheaper than the e-Golf. So the TCO analysis showed that investment costs of the vehicle itself had the most significant impact on the TCO. Norway and the Netherlands show that the dissemination of BEVs is the highest in countries where proper policies are installed. Norway has the highest BEV market share worldwide. Nevertheless, TCO for BEVs are very high. The Netherlands has a similar situation. Instead of many non-monetary measures, high subsidies are granted. So it can be summarized that high registration taxes and fuel prices in combination with low electricity prices and non-monetary incentives and subsidies on the purchase price are highly effective for the promotion of BEVs. Regarding the sensitivity analysis, the result is that the change in the interest rate parameter had a stronger effect on the annual costs than a change in the depreciation time. In conclusion, yeah, let me sum up my main points. Low costs for BEVs alone do not ensure high BEV dissemination. Nevertheless, high prices are still a barrier. So non-monetary incentives combined with high registration taxes and high fuel prices are highly effective. Incentives such as low electricity costs should always be linked to their incentives such as high fuel prices. So finally, the following recommendations for policy makers to reduce CO2 emissions are summarized. Offering subsidies on the purchase price of for BEVs, implementation of high registration taxes for ECEs, introduction of legal frameworks for the introduction of emission-free zones and free parking for BEVs. And finally, the introduction of CO2 taxes. That's it from me. So thank you so much for listening. And are there any questions?
Thank you very much for your presentation, Marina. For the moment, I don't see any hands raised in the Zoom, but I have some few questions. Sorry. Just the first one, maybe not the easy one. You mentioned at the end that one of the main solutions to develop EV market should be to have an increasing of taxes on gas. Yes, yes, high price. Yes, highest price and taxes on traditional energy for ICE, and to not to have so much incentive. But do you think that this kind of policy with the lowest gas consumption can have an impact of the country's economy? Because we have the case in France, if you reduce the taxes, actually, for the moment, currently catch by the state on the diesel and traditional gas. If you reduce it a lot, do you think it could have a huge impact on the economy? Because if you don't add tax on electricity, for example, just to continue to develop the EV market, do you think the equilibrium will be changed in that case? Am I clear?
I'm not, it's not fully clear, but I tried. So, sorry?
Oh, good. Yeah, let's go.
Okay. So I think taxes have a huge impact on the price. So as I showed as an example, Netherlands. There are I'm not sure if you see my
Yes,
mouse.
that's good.
Oh, yes, yeah. So
yes.
The green part are the costs for the energy, and I think this is a huge part of the costs, and also so I'm a fan of CO2 taxes, and I think they do this is a huge factor. Yes.
Okay. No, I mentioned that because in France, we few years ago now, we had a try from the public authority to increase the tax on diesel and so on, and after we have a large part of the population using a lot their car, but traditional car because they have not enough money to buy EVs. Began to be disappointed, and we start with the yellow jacket events and lots of riots and something like that. So it's why we are quite sensitive in France on the of a tax on traditional fuels. And even I agree with the fact that if you reduce or you increase the cost of traditional fuel compared to electricity, it should be a good opportunity to accelerate the integration and the development of the EVs, for sure. Yes, in your you said in your conclusion that you mentioned investment cost of the vehicle. What does it mean? Yes, in the first sentence you made investment cost of the vehicle. Is it the cost invest by the customer, or is it the cost invest by the OEM producing the car?
No, this is from an individual perspective.
Okay.
Yes,
okay.
It's the purchase price.
Yes.
With subsidies on the purchase price. Yes.
Yes, it's still a huge problem, of course. Is there some question? I don't see any hand raised. Yes, you mentioned that, but I think I've got my answer. But in your paper, you mentioned that you are focused on the greenhouse gas emission reduction, focus on the transportation and using battery electrical vehicles. Do you think that if the country, any type of country, has a more overall policy to reduce the global greenhouse gas emission for all the industries, it should have a positive impact at the deployment of this kind of electric mobility? If it just focus on, yes,
I'm not sure if I get the question.
Now, of course, if a country decide to promote electric transportation to reduce CO2 emissions and something like that, that's good. And do you think if the same country has a more overall vision of the CO2 emission, but not just for transportation, but also for industries, energy producers, and etc., it should have also a good impact or a help to develop the EV market?
Yes, sure. So CO2 taxes should be implemented for all of these fields. Yes, energy industry, agriculture, all. Yes.
Mm-hmm. Okay, I think it the main words for your presentation, it's focus on taxes. And it's sure that no, it's a fact, and we observe that sometimes it's a good solutions to help people to accelerate the change of mind, because it's difficult to come from a solution to go for another one with a range, autonomy, anxiety, and something like that. So it's why taxes sometimes it's useful.
Yes.
There is a hand.
Yes.
Yes, please.
Yes, I raised a hand. So I have a couple of questions that are very probably too general. So first of all, you said at some point, well, you mentioned that Norway doesn't have any subsidies on vehicle purchase anymore. So until up to one point, according to maybe to your analysis or to what you've read, is it okay to stop subsidization in the sense that subsidies are effective but costly? Yeah, so is there some light on that?
Norway has no subsidies on EVs or BEVs. You're right. They are doing it good. They have a lot of non-monetary measures, and it balances itself out. So Norway has the biggest market share and a huge amount of BEV sales. So they are doing it great. So we don't need subsidies. So Norway shows this, yes.
Thank you. Is there other question to Marina, or if there is no more question, we can. I want to thank warmly all the speakers for this session. Clearly, even it's a session located in the end of the day, so it's not the most attractive maybe, but I appreciate to have a very various type of presentation and different point of view according to the storage, which is a very large problem, not only technically speaking, because I'm more on this part of the activity, more on technical activities, but it's still interesting to have this vision around the competitiveness, the availability of the raw materials, and also the business around these sensitive materials, and also finally to try to develop and to help to have a less CO2 emission transportation solutions. So I appreciate a lot all this presentation. So thanks again. And also I want to thank people who follow this session. And if there is nothing else to say, maybe from the host, and then nothing more to add.
No, just thank you for your participation, and I hope you enjoy it.
Thank you. So have a good end of day for everyone, and maybe see you soon.
Thank you.
You
Thank
too.
you. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye-bye.